Initially, you were not convinced that you should put iron in order to grow diatoms.
Yeah,
So John
yeah,
Martin didn't convince you, but then new data made you change your mind.
yeah.
So
The experiments made me change my mind that his group carried out. So there were two things here. So in that period when John Martin, he was the visionary. He was a biologist by training, but he then became a geochemist, became a chemist, and he was working in chemistry. He realized early on that it was iron. That was the reason why large areas of the ocean have very high nutrients throughout the year. So this is unthinkable. In Kiel Bight, the nutrients were there during the winter, then the spring diatom bloom happened, and the diatoms took up all the nutrients. The nutrients went down to zero. You could down to the level of detection. And after that, the system changed completely because then this was a recycling system. So there were no new nutrients put into the system. But then in the Antarctic, when I got down there and we made our measurements, okay, I knew that this was very well known. It's still there, this situation, that you have very high nutrient concentrations, but nothing's happening. Right? And to explain that, I thought, yeah, because it's so cold and it's so windy, and meaning that the mixed layer is very deep, so they don't have enough light, and then there are all these zooplankton around, and so they somehow don't manage. This is a couple of years I thought that. But then I started getting more and more evidence that there had to be another factor, and it was iron. Right? And when I started putting iron into my picture, then things started changing. They started making sense, what we were seeing. And what I didn't believe was that if you added iron to a patch of water in the ocean, that you would be able to follow it. I thought that it would immediately be dispersed and you wouldn't be able to run an experiment. That is what kept me from believing this. But when the results of the first experiment, they were friends of mine on that experiment. When I heard about that, before that I was making fun, it's not going to work. But when they showed that it did work, I was changed. That I had a click, and so we have to do experiments too. And then the second experiment, a couple of years later, was even more convincing, and it was great. But I have to mention that the friends who were on those cruises, or with whom I talked, they were so shocked by what had happened. Shocked in the sense that they put iron into the water, and suddenly that water came to life. Fish started moving, jumping around the place. The water became green. And it was just like, oh my God, what have we done? Feeling like as if we'd done something terrible. Instead of the other way around, that we had done something fantastic, that we had now discovered a lever with which we can turn things on and off in the oceans. And that iron plays the same role in the oceans that water does on land. Right? And the iron in the ocean is most of it, 60% of the iron in the open ocean is provided by dust. Right? And dust rains, just like rain. Actually, it comes down with rain. Right? The dust is in the air because it's swept off the continents and it gets swept up in the upper troposphere. It gets transported around the place and then it gets washed out. And when the first ice core measurements were made, where they measured the CO2 concentration in the ice core, the CO2 concentrations in the air bubbles in the ice cores that had been trapped as snow. They also measured the dust, and they got a very tight correlation between the concentration of dust in that level and the concentration of CO2. So when there was a lot of dust, there was less CO2. And that meant that the phytoplankton had got this dust, they had done their photosynthesis, they had grown, and they had taken out carbon dioxide from the atmosphere. So there was this relationship was very clear. And with the experiments, I then realized that we had discovered a whole new set of rules that ruled by iron rules, you might call them, that were running the open ocean. And they were quite different to what was happening along the coasts, where you had enough iron. Basically, my feeling was that the coast is the place where the action is taking place. This is where all the fish are and all the productivity is happening, and all what we call good things about the ocean are happening along the coasts. And the open oceans are barren. There's nothing much happening there, except for places where there are islands and where the barren ocean water comes into contact with iron from land masses. So yeah, there you are.
Yeah. So this might be a good representation. So this is like 2002. I think this is in the beginning of the first iron ocean fertilization experiments. And what you're describing is exactly that, right? So you have basically all the phytoplankton activity around the coasts, and it goes now month by month. So we have 20 years of data through NASA. And I guess what you're describing is the further you're away from land, the less phytoplankton productivity.
Just notice what the North Atlantic looks like. The North Atlantic looks quite different to the other oceans at the same latitude. It has much more green, like that. That's the spring bloom of the North Atlantic. So a lot of people have been working in the North Atlantic because of the US and Europe. And the North Atlantic is different. The North Atlantic has all that dust from the Sahara. See, if you think
so now we're looking at August 2011. We can also just go into August 2023 and just say, what's the picture today? Like a year ago, this was the phytoplankton productivity.
There's an unusual amount of green in the North Pacific, I must admit. But there again, you have periods where they have more dust coming from the Asian continent. They don't have the kind of dust that the Sahara has. And North Africa is this huge reservoir of dust, by far the largest on the planet. And if you go to South America, which would be, of course, 6 months later, to compare, they are having the winter now. That if you go,
so that would be February 2024.
Yeah, see, there's nothing going on there because there is a desert, but it's the Atacama Desert, and it's just a narrow strip. It's a few tens of kilometers wide, or perhaps 100 or so, along the coast of South America, because the Andes are there, right? So you don't have anything comparable to the Sahara in the other places. A little bit in Australia, but again, it's a question of winds and wind directions and so on. The eutrophication, you see the eutrophication along the Chinese coast, probably, if you go back 20 years or so. Oh, but let's not do that now. That's nitrogen and phosphate, whereas the iron is due to dust. So the dust is whipped off the continents and deposited in the ocean. And there was about 10 times more dust during the glacier, during the last ice ages, than there is now. Because we tend to think again of the rainforest of South America, the Brazilian, we say Brazilian, but it's much bigger than Brazil. That rainforest is a very kind of permanent structure. It's not. 15,000 years ago, during the Ice Age, at the end of the Ice Age, large parts of this rainforest were savanna. There was a lot of dust blown off South America, for instance, but also the other continents. So there was much, much more dust in the air, much more iron. And one can put it together in a nutshell and say when the land is brown because of droughts, there's rainfall. When the land is brown, the oceans are green, and vice versa. And now we are entering a phase where there's more rainfall, but that rainfall is also much more concentrated, meaning that it's focused on fewer, larger, smaller areas, meaning that there are areas that are left out.
Yeah, so let's get into the numbers. Would love you to maybe just fantasize with me, and let's just say a ton of iron is purchasable at, let's just say $10 per ton. I think that's something probably you had in mind, since it's a waste product, as you explained in your presentation.
But remember, of course, the markets are like that. But the moment these people smell, the people who have the iron, when they smell that, there's a demand, then the price will go up, of course. But so I'm not going to make any statements here about the current demand, but I can just say that until recently, not recently, but until the 1970s, we have a factory here opposite from our institute in Bremerhaven, which is a titanium factory. And it's called Konus Titan. And they had two ships that every day were going out individually. One ship went out, the other one came back. And they were dumping iron in the North Sea. right? They were just dumping it. They were going out and leaving it, just dumping it. And yeah, so this is the iron that they sell now. And this, while they were doing this, was discovered by Greenpeace, and Greenpeace moved in and made a huge propaganda activity. It was okay. They just said that, see, all this iron being dumped in the North Sea is going to harm the North Sea. But to tell you the truth, there was no effect. There was also the institute here. This is before the Alfred Wegener Institute was founded. They had been studying this and they could find no effect, because the iron in the North Sea is like adding water in a lake. You don't get more plants growing because it's already water there. And the North Sea is very rich in iron because it's shallow, it's sediment, has a sedimentary bottom, and every storm that goes through the North Sea resuspends iron. So there's a huge amount of iron in the North Sea, and then you add iron on top of that, it had no effect. So the plankton didn't grow nothing. They couldn't find anything. Okay. As I said, they had 2 ships going out and dumping this stuff. And then they were told to stop doing this. And it was prohibited. And then nobody asked, what are you doing with the iron now? Right? And what they did is they converted it into bags like you see in this picture here, and sell it as for gardens, for gardeners to put on their lawn, because it kills the moss. And it kills the moss. It's not by toxicity, but the moss overgrow. They grow wild, and then you can just rake them off. And the grass loves that. So the grass thrives on the iron, and all the other plants also thrive on the iron. But there are few places on the planet on land that are iron limited, because the soils are all very rich in iron. Anyway, that was one use for this, and the other use was for sewage treatment plants, where they would add the iron to precipitate or to remove phosphate. That was all right, so nobody made a fuss about it anymore. But still, they are not getting like huge amounts of money for this iron. And I actually have a bucket of iron fertilizer here.
Yeah, would be nice to look at.
Yeah, can you? It's not focusing. That's the problem, right? You can't see it, no?
Yeah, now it's focusing. Yeah.
Anyway, so this is 5 kilograms, and it's for about 200 square meters of lawn. 5 kilograms for 200 square meters, right? Now, to get the plankton going, you would need for 200 square meters about 1 gram or so, right? Remember, this is ferrous sulfate, and only 1/3 of that is iron. The rest is sulfate, is a very heavy anion, and there's also water crystallization. So about 1/3 of the iron that we added was actually iron, elemental iron, right? The rest are the salts. When iron is taken up, the demand for iron is also, the optimal demand is species dependent, right? Like, for instance, we have a ratio of carbon to iron of 8,600 actually. And if you convert that now into weight, the carbon to iron ratio, each of us is walking around with 4 grams of iron. 4 grams of iron. Now, of course, 4 grams of iron, elemental iron, it doesn't tell you much. But iron has twice the weight of water, the density. So 4 grams of iron is equal to 2 cubic centimeters of iron as in volume. So imagine 2 cubic centimeters, that is the amount of iron we contain. And we need iron. I mean, we mammals, warm-blooded animals that have hemoglobin as an iron carrier and all the other purposes that we need iron for, we have a very high demand for iron. And it's probably similar to the whales. They probably also have this 8,000 ratio in their biomass. But the phytoplankton, they can do with much less iron, and they do actually with much less iron. So the ratio of iron depleted biomass, that means phytoplankton that has finished its reserves of iron, it's practically stopped growing because it doesn't have any more iron, that would have a ratio of above 50,000 to 1. And in the laboratory, we measure 100,000. Now, these are algae that are not growing. They've reached that level, and then they just stop over there, right? You add more iron, then they can start growing again. The ratio of carbon to iron in phytoplankton is above 50,000. And during our experiment, we calculated a minimum of 15,000. That's what we actually measured. We put in that much iron, and assuming all that iron has gone into the phytoplankton that we measured, then you come to 15,000. But in reality, we missed a lot of the phytoplankton, and it was definitely higher. It's closer to 30,000. And that was at the time when we had built up the biomass. So after we left, there would have been more biomass built up, and that would have led to more carbon being fixed, right? So this 15,000 to 1 is a very conservative estimate. And even 30,000 to 1 is also still conservative. And what you would expect is actually closer to 50 to 100,000 to 1 is what you would get if you add iron, of carbon to iron.
Right, there's no iron loss.
No. And I think that over the course of time, the iron-carbon ratio because it's a bottleneck for organisms living in aquatic systems where there's no additional source of iron, that is highly efficient. They take up that practically all the iron that enters in a dissolved state, like ferrous sulfate, is taken up. And that's not surprising because there are a huge number of molecules, organic molecules, that have evolved to take up iron. I think I talked about this last time, but there's this relationship between pathogens and hosts, like we ourselves. We have less iron than we need because we don't want to give it to the pathogens that would then take it up, because our pathogens are limited also by iron. The story here is that iron that is added to the ocean by dust or by artificially by us or by whales, that iron is utilized, very well utilized, but eventually it gets lost. Specifically lost. The iron element as an element sinks out with these particles that are sinking out. And that iron is then lost and has to be replenished. It's not recycled the way nitrogen and phosphate are recycled. And that's because iron is so insoluble. Iron 3, ferric iron, is highly insoluble. So that's why it gets lost and has to be added again. Anyway, so there are large stretches of the ocean called red abyssal clay that contain a lot of iron. And that just shows the only element that is really lost is iron, because these are the poorest sediments on the planet. There's nothing else there. It's just red abyssal clay, and that's dust, fossil dust with iron.
Another interesting approach that I've talked to people about is what other ways are there to transport iron to the ocean? So obviously we know that dust is one of the main source for iron into the ocean. Do you think it's possible, instead of using iron sulfate, to collect dust and distribute dust into the ocean? So
why would you want to? Because dust, like 10% of the planet is iron. And whatever you take, then take pure iron. If you have taking anything anywhere, then you take the pure iron, because ferrous sulfate is by far the best way of adding iron to the ocean. It's also the way the pills are made out of against anemia. I've also taken a whole course. I must have eaten 100 pills of milligrams of ferrous sulfate to counteract my iron deficiency.
yeah. So you spend too much time in the Southern Ocean. The iron deficiency spilled over to your body, and you're iron deficient
Yeah,
too.
see, I was on the ship and we were throwing iron all over the place, and still I developed an iron deficiency.
I guess the reason people are looking for organic materials that contain iron, that are not iron sulfate, is to prove a point to the public. Obviously, long term, we should choose the most efficient way to transport iron into iron deficient areas of the ocean. But the idea of dust and other materials that contain iron that are natural is to calm down the scaremongering, to show them This is a dust that is in the air anyway. All we are using is dust. So it's the same thing that is happening like hundreds of kilometers further on. It would be much more expensive,
Yeah,
operationally much more complicated, but it may create an easier path to permits, because whatever you put in the ocean, it's not coming from a factory, it's coming from nature. And that's the idea some people in OIF have.
but we have to say, I know, but this is also because of the stories that not all the iron is taken up and all that kind of stuff. I think we mentioned that earlier, that there are a lot of phytoplankton species on cells at a given time that can take up a huge amount of iron and keep it. And that's why they thought we should use alternatives. And these alternatives are, I think they're crazy because they're not going to help. You just carry a lot of other stuff along with you in this red mud and so on that people want to use. And that's all pointless. It's just beating around the bush. And if you say that the treatment against anemia is ferrous sulfate, you're eating that damn stuff and it's going to harm the ocean. We are eating it. The individuals, the doctors prescribe ferrous sulfate. And this is what these iron people don't know because they haven't had that experience themselves. So they think that, oh, ferrous sulfate is a chemical and shouldn't use it. And this is ridiculous. I think if we can convince people just that we have to add iron to get the ocean life back, then we should also say that it's ferrous sulfate because it brings us anemic people also back to life. So going into other so-called natural sources of iron, in the end of the story, it's ferric or ferrous ions, meaning molecules, atoms and molecules of iron that we are adding and putting them in the form of dust and all that is ridiculous. You have to go and dig all that dust, carry it there, sprinkle huge amounts, and come on. We already have the very simple, clean solution. This ferrous sulfate is very clean. It's allowed for putting on lawns to improve lawns. So it doesn't have all those other heavy metals and all the other contaminants that dust would have. Dust is also has all sorts of other complications. And why would you want to use dust if you have ferrous sulfate, which you can dissolve and add? And it's proven that it works. We showed already that most of that iron that we added was taken up. So
Interesting story is that one of the scientists of the Canadian experiment that was controversial, he's actually now using iron for plants on shore. So he couldn't find any path to be active in the ocean with iron, but he figured out the same thing that you just mentioned with plants.
yeah, because iron is a very interesting element because it's a completely different kind of element. I'm writing this up. It's a completely different kind of element to the others that we know. It has a different background and so on, right? We have proteins in our blood. I mentioned this earlier, where one protein can pick up 4,000 atoms of iron and keep that in a cage. At 4,000 atoms of iron, one protein molecule. You can have limitation. And there's a paper came out a couple of months ago in Nature showing that plants are also fighting over iron. So that's why this person you're talking about, who's adding iron, he is preventing this from happening. You know, the story I said about the blood being iron limited. So the soils can also be iron limited because of this arms race story going on, that plants are withdrawing iron from their competitors. So I can imagine that it would have some effect, no, if it's done properly on land.
Now, ferrous iron salts are soluble, the reduced form of iron. But under oxic alkaline conditions, you get the ferrous is oxidized to ferric, which combines with oxygen and water to form highly insoluble ferric oxide or hydroxide. This is a complex molecule. It's not just a simple FeOH3, because there's also Fe2O3 ferric oxide. It's a mixture of these different ferric oxide hydroxides. Now, iron binds to a broad range of organic molecules that are called ligands that pick up iron. And they can maintain iron in solution. It's organic iron then. No? And siderophores are one example, are ligands formed by bacteria that bind iron so strongly that other organisms cannot utilize them, for instance, right? So there's a huge iron biology. The biology of iron is a whole new complex which is just opening up now, which we are beginning to understand. Lactoferrol, for instance, is a glycoprotein deployed widely in saliva, blood plasma, etc., to limit growth of pathogens. And ferritin is a cage-like storage protein that can hold 4,500 iron atoms. It has like a needle. Inside one molecule, one protein molecule, there's a needle of iron atoms, and 4,700 can be contained in this. No? And transferrin, which is another protein which picks up iron and carries it to the ferritin to bind it and hold it, no? Provides the iron. Both molecules are reported to occur in all organisms, from archaea to mammals. And the complex iron chemistry in seawater is under study. And the reason why this became so late is because contamination is a serious problem. Because iron is everywhere. So if you want to study the situation where there's no iron, you need to take extreme precautions. You have to have ultra clean conditions, because iron in our world here is everywhere. And even then, that 30% of the population are suffering from anemia, iron deficiency. And I have also been diagnosed at one time with iron deficiency a couple of years ago. We are just beginning to understand the critical role of iron in biology. Now, when I say here that iron is bound by these ligands, I give you an example. I give you some examples now about the impact of iron on organisms. For instance, a classic case is your mouth, our mouths. You know that we have wounds in our mouth quite often, because when you're brushing your teeth, for instance, right? If you do it too strongly, you get bleeding and so on, and other instances also. But how many of you have had an infection in the mouth? It almost never happens, right? Whereas if you have a cut in your skin or something and you don't treat it, you get a pus infection, right? But that never happens in the mouth. And the reason is that the mouth is iron limited, right? The bacteria in the mouth, they cannot grow because they cannot get hold of iron. And the reason why although you're eating so much iron all the time, right? But that iron is immediately bound by these proteins, lactoferrol, for instance. It was discovered in milk. That's why it's called lactoferrol, but it's all over the place. And these lactoferrol molecules, they also played an important role now. Not an important, but it came up with COVID, that they also, this is part of our immune system, if you will. The other thing is blood. If you just think of our blood is a heaven for bacteria. It has everything, right? It has dissolved oxygen. It has all the monomers you can dream of, amino acids, sugars, and everything. But still, there are very few organisms that grow in the blood, pathogens. And which is the most well-known? And it causes lots of deaths. Malaria. Right? The malaria parasite, it's a protozoa, no? Plasmodium. And it's injected into our blood by mosquitoes. And then what happens? These parasites, the malaria parasites, they go into red blood corpuscles, because that's where the iron is, right? So the plasmodium, the infecting plasmodium, they go into red blood corpuscles, and there they then have this iron supply from the hemoglobin and all the other plasma, and then they grow, they multiply, and then they burst that blood, the red blood corpuscle, and enter the bloodstream. And that's when your body recognizes that you have that, and that's when you get the fever. Now, the fever is the body's way of defending itself, right? Because then you mobilize more resources and then you go for those parasites. And then what happens is that those parasites, the first ones that enter your blood, They cause this fever, and then they all go back again into hemoglobin because there's no point of them hanging around in the blood by itself, because what they want is to be taken up by a mosquito that will then transfer you, not spread them. This cycle goes on, and that's when you get these bouts of fever, and then it goes away again because then all the parasites have gone back into the red blood corpuscles, and then they come out again, and then you get these bouts. So they cannot grow in the plasma by themselves. They have to go into living tissue to get the iron, because the blood plasma is also iron limited. And this, of course, applies to all organisms. I just read recently, there's a bird in Hawaii which is becoming extinct because it's been infected by malaria that was introduced to the island. And this bird is not immune, it cannot cope with it. And malaria is still one of the biggest killers on the planet, because of this. And this is the cycle of malaria. So all the other possibilities, pathogens, right? They haven't figured out the iron issue. So you see, this is one example of how iron controls us. And then, of course, the malaria parasites also go into the liver and hide over there. And then they can come out after a year, 2 years or something. I've seen people who got malaria, who had a malaria attack in Germany, and they'd come from Pakistan, for instance. There was one person. And after spending a year here, he got malaria. That's because the malaria came out of the liver, where it had been hiding. So that can happen here also. And of course, the doctors didn't know what it was, why this guy was having this very high fever and then nothing. Because when the doctor came to study, there was nothing. The guy was okay, right? Because it was between the bouts of fever. And it was not known at the time. But now, of course, it's better known. So when tourists come from malaria areas, regions where there's malaria, they can get it. By the way, malaria was very widespread also in Europe. There was malaria also in Holland, for instance. And there's a term called drain the swamps. This is what the people in the US are using. So why do you want to drain the swamps? Because that's where the malaria is. And that's what, I read this. This is also what Mussolini did in Italy. In Italy, the very picturesque villages, they are up on the top of the mountains, and right up at the top, the fields are below. And of course, it's very picturesque, looks nice and so on. But why don't the people build the villages below? Because there was malaria. Right? Whereas up on this top where the villages were built, there you had winds, and that blew away the mosquitoes. And then I have a little hypothesis of my own about this, that why big churches were built. Because in the churches, the swifts. Swifts used to nest. And the swifts eat mosquitoes. I haven't read about this anywhere, but I just think that's why all the houses were built very close around churches, because that's where the swift swarms would go out and eat all the mosquitoes. And so there was less mosquito incidence in those places where they built the villages than it was down below. And the word malaria, malaria, is actually Italian. No? It means bad air, because that's what people thought, that it was breathing the air of the swamps that gave you malaria. And the malaria parasite, by the way, was found in a little town not far from where I grew up. It's called Almora in the Himalayas. And there was, I forget his name, I think it was called Ross was his name also, who discovered the malaria parasite by studying the blood of people, right? So where I grew up also, it's the same story. The people would go down to the flatland, the Tarai, in the winter season, and during the summer they would go up to the mountains. And that was to avoid the malaria. So this malaria pathogen is a different species of malaria, but they are so successful because they know how to control the iron supply, by doing this thing, by going into the red blood cells. But then there are also other species of bacteria that are very dangerous. The bacteria that can cause, that can lead to very rapid death. They explode. And what they do is they break down living tissue. That's where they get their iron then from. These are the very common infectious bacteria that we need antibiotics against. And anyway, so they attack living tissue, and that's where they get the iron from. But otherwise, the plasma, our blood plasma, saliva, all our body fluids are iron limited by these molecules. Yeah, and you also get this ferritin, for instance. As I said over here, it's in all organisms from the archaea to us, but you don't hear much about it, not yet. Now, what is the function of this ferritin? In the past, we were in a soup of iron, ferrous iron, right? Because the entire surface of the planet was reducing, right? This is in the pre-Proterozoic, in that period, no? The Archean and the Proterozoic, when there was no oxygen in the air. We were living in the soup of iron, ferrous elements. And iron then, because it was so freely available, it was everywhere, it was used as the major metal for all sorts of enzymes, for instance, and all sorts of processes that were based on iron, which is why we need iron so much because we evolved in an iron-rich world. And then, when the surface of the planet became oxidizing, iron went into short supply. No? The deposits of iron ore that are on the continents all over that you find, they sucked up a lot of oxygen that was released by the cyanobacteria. And that's where this iron was precipitated out of the water on the surface of the planet. So iron got into short supply because it was removed by the oxygen. So the other side of the coin of the oxygen, we got more energy, but we also lost the iron. So this ferritin and these iron molecules, they were originally evolved to keep iron at bay, the excess iron. Because iron is very reactive and it had to be kept out of chemical reactions. And that's why they had to evolve these molecules to control the iron. There was too much iron at that time. Now it's the other way around. Now we have too little iron because the world is oxidizing and ferric ions are highly insoluble. And now we have a different problem with iron than we had in the past. It was when there was too much iron. Look at this, right? This is a dust storm over the Sahara distributing iron over the ocean. So you see now how much dust the North Atlantic is getting. Huh? Because of this huge area, we get sandstorms from the Sahara here. No? You can see it settling on the cars, as a matter of fact, as far as Kiel, right? I mean, way up there. But that's sand, and that sand doesn't have much iron. The iron is in soil, dried soil in which plants had grown before. They had rooted, and the Sahara was green 5,000 years ago. Green means that there was grasses, there were a small scattered forest, savanna. There was a very kind of thin type of savanna in the Sahara. And then it dried out again. And now, of course, it's the dry Sahara that we know. But the soil, the dust from the ocean, that's what contains the iron. Now, just to give you a feeling, these are data from modeling. This is the dust input today over the ocean, and from Patagonia, for instance, and Australia, South Africa, but of course here the North Atlantic has a huge amount of dust, where you can see how much dust from the land was deposited. This is what it looked like in the glacials. This is the difference. So you had much more dust. The atmosphere was much dustier. There was much more dust deposited in the ocean. And therefore, it makes sense that, for instance, this region here was much more productive than it is today. Yeah?